In this short video, we're going to learn how to make educated estimates about very different types of situations. So these are sometimes called Fermi problems after the famous physicist Enrico Fermi, who is well known for being very good at these sorts of estimates. They're also sometimes called back of the envelope calculations because they can just be done quickly without calculators or looking up a lot of resources and numbers. All right, so let's think about some of the features that make something a Fermi problem. One is that they mainly deal with orders of magnitude. And when we say orders of magnitude, what we mean is things that are, say, on the order of, 10 to the third, or on the order of 10 to the minus 3. And so you have some very, wide range for your final answer in terms of what that might look like. And so we're not really going for a specific number. You're certainly not going to have more than one significant digit. Sometimes answers might look like something, where you might say, okay, I'm ending up with 4 times 10 to the, whatever power it might be. But it would again be that it's on the order of that. So we're really just looking at it to be within a power of 10. So you've basically completed a successful Fermi problem and a good estimate if your final answer is within a factor of 10 of the real value. The other thing is that you have some educated guesses that go into the original calculation that you're going to do. And then you use those to do the calculation. So it is not just a wild guess at the final answer. There is a calculation involved, but it's one that can be done with mental math. So these Fermi questions can be really useful in everyday life. So here's some examples that I've found. So for example, in business, if we look here, how many teens live within 30-mile radius of our proposed radio station, right? So maybe you care about that in terms of marketing. Maybe, you have to, figure out whether or not that's the population that your radio station is going to cater to or not. Environmental policy, educational policy. If a school district reduces the maximum class size to 20 students, how much would it cost to hire the extra teachers? Really fundamental questions. Right now, when we're all trying to figure out social distancing and how that might look in schools, there are going to be a lot of these types of estimates and calculations going on in everyday life. All right, so let's go work through an example ourselves. And so the example I'm going to work through is, let's say that we have all the people in the entire world and we crowded them together. How much area would they take up? So how much area for all people in the world to crowd together in that? So the crowding together, that's going to be where our estimates come in, right? Because we kind of know, or at least we can estimate the world population, certainly to a factor of 10. It's 7.8 billion at the moment. So I'm going to write that as the number of people. So first I'll write down my assumptions. And this first assumption here would be that there's just about 8 billion people, right? So 8 billion people. And so again, that's 8 billion would be times 10 to the 9th. So 8 times 10 to the 9th people. So this is going to be one of my key assumptions right there. Now the other one, and that one was based on facts. The other one is going to be an educated guess. This is really where I am making an educated guess. I'm not just randomly guessing. I'm imagining taking a bunch of people I know, tall people, small little kids, crunching them together and how much space they might need. And so what I'm going to do in order to figure this out is say, well, okay, let's figure out how much space one person on average might need. And because, we're in America and we're not as used to the metric system, my initial feeling on that is that we would maybe need just about 1 square foot per person, right? We could maybe squish all into that, especially if we count the small little kids, and we all squish in. So 1 square foot per person, but I want to work in the metric system. And so now I'm just going to convert that. So if I say here 1 square foot, so what I can do then is just imagine what that might look like. A square foot, 1 foot on the side. Well, I know a foot is about 1/3 of a meter. So I would have 1/3 of a meter over here and 1/3 of a meter over there on my square. So 1 square foot is actually going to be around 1/9 meter squared, right? Because 1/3 times 1/3 and then 1/9 meter squared. And I'm dealing with orders of magnitude. So what that means is this is 1/10. So that's approximately 1 times 10 to the minus 1, right? So that's a way of writing 1/10, 0.1 meters squared per person. So this is now my other main estimate. And now I'm ready for my calculation. So now I do the calculation step using these values. And this is basically 8 times 10 to the 9th people. And you do it the same way you might just do a unit conversion or something like that. So, and then I know how many meters squared per person. So 1 times 10 to the minus 1 meters squared per person. So that lets me allow to get rid of the person unit. And I'm left with meters squared. So 8 times 10 to the 9th times 1 times 10 to the minus 1 is simply going to be equal to 8 times 10 to the 8th meters squared. And so order of magnitude now, 8 rounds up. And so this will be on the order of 10 to the 9th meters squared total. So technically that's my answer. Oops, I erased it. I'm sorry. So let me write that here. So around 10 to the 9th meters squared total. I meant to highlight it. So in that case, that's our answer, but it's always good to put it in context. And again, since we're not as familiar with just imagining what 10 to the 9th meters squared might look like, square meters, or even square feet would be like hard to kind of visualize how much space that might take up. And 10 to the 9th seems like a really big, giant number. So, is that as big as the state of California, or is it like, as big as my backyard? So let's try to figure out and visualize 10 to the 9th meters squared. So in order to do that, we can imagine what it might look like. Again, if I just imagine having a square, that the area was 10 to the 9th, then what would be the sides of each of the squares? And it'd just be the square root of 10 to the 9th. So, if you think about that, then 10 to the 8th, that'd be 10 to the 4th times 10 to the 4th. And then you have an extra 10, square root of 10, it's about 3. So the sides of each of these would be around 3 times 10 to the 4th meters. So around 3 times 10 to the 4th meters on a side. And again, you're like, oh my gosh, there's a 10 to the 4th, it's so big. But what that really is here is if we look at that, in terms of kilometers, which is more familiar, it's something people run 5Ks all the time, right? And so you have 3 times 10 to the 4th, that's really just going to be 30 kilometers. So this would be 30 kilometers on a side. So kind of the size of a small city, right? Or a small town, right? 30 kilometers is pretty easy, short, relatively short drive, right? And you just imagine taking those sides of the square and then all of our little people squished in, be very unpleasant, the 7.8 billion people, that's the rough area of what they would take up. All right, so that ends this video on Fermi problems.